Now let's look at the procedure for diagonalizing a matrix. So there are 3 steps that you need to know how to find out the matrix that diagonalize a matrix P. So the first is to confirm whether the matrix is diagonalizable or not, so which can be determined by the number of bases for the eigenspace and the number of unknowns. The number of bases for the eigenspace must be equivalent to the number of unknowns for the matrix A to be diagonalizable. Then you form a matrix P which consists of all the bases that you have found out from the previous step. And the last one is to express P inverse AP in the form of diagonal matrix, where D is the diagonal matrix with the lambda, which is the eigenvalues, as the entries. So basically, you just need to rewrite this expression. You don't need to calculate what is P inverse AP, because this definitely will give you the diagonal matrix if you get the correct eigen vectors. So let's look at one of the example here. Find a matrix P such that it diagonalizes the matrix A. So remember, the first step is you want to check whether it is diagonalizable or not. So you use the characteristic equations here, which is written in this way if you couldn't visualize it. So you will find out that the lambda is 1 and lambda is 2. And then you substitute into these equations lambda I minus A multiplied with x equals to 0 to find out the bases. Okay, if you forgot how to find out the bases, try to watch back the previous lesson on how to find the bases for all the eigenspace. So you have the corresponding P1 corresponding the eigenvector corresponding to the first eigenvalues, and P2, P3 corresponding to the second eigenvalues. So the third step is quite straightforward, where you create a new matrix P such that it is a combination of the P1, P2, P3, the bases of the eigenspace. So the sequence of the P1, P2, P3 here, you can rearrange the sequence such that you have a P2, P1, P3, or P3, P2, P1. The sequence doesn't matter, as long as in the third step, when you rewrite it in this form, the diagonal matrix here, the entry here must be corresponding to the column vector or the P here. So the first P1 corresponding to lambda equals 1. So when you move P1 to the second column or to the last column, the corresponding eigenvalues will move with it. So my advice is that try to stick with the labeling here. If you have P1 corresponding to 1, so you're just going to put P1 as the first column, P2 for the second column, and P3 for the third column. Because no matter how you arrange the sequence, either P2, P1, P3, or P3, P2, P1, your final answer here will look like this, where the entries are the eigenvalues. And we have some cases where the matrix is not diagonalizable. So let's look at this matrix A. I found out that the eigenvalues is 1, correspondingly with the eigenspace, which is this one, and another one is 2, and with 1 eigenvectors. So we only have 2 bases for the eigenspace, while we have 3 columns or 3 unknowns. So remember the conditions in the step 1. The number of bases for the eigenspace must be the same as the number of columns or unknowns. So in this case, since they are not the same and A is not diagonalizable. Or alternatively, if you just want to know whether the matrix is diagonalizable or not, you don't need to solve until to get the bases. Okay, you just use these conditions, lambda I minus A. So the lambda will be 1 here, just need to substitute here, and then you reduce it, you'll find out that the rank is 2 and nullity is 1. So the rank is, remember, the dimension of the row, or the number of leading one here. So remember the lessons that you learned in chapter 4 about the rank and the nullity. So you don't need to find out the nullity as well, because the nullity is actually the basis for the AX equals to 0. In this case, it's the I minus A. Because if you know the relationship here, rank plus nullity equals the number of unknowns. So once you have the rank, you don't need to find the nullity because you can just use this equation to find out the nullity. And then you do the same for the second value of eigenvalues. So the total bases for the nullity is 1 and 1. So you have 2. And the unknowns is 3. So it is not equivalent and A is not diagonalizable. So in this case, you don't need to find out the eigenvalues and you don't need to find out the basis for the eigenvectors. So the tip is that if an n by n matrix A has n distinct eigenvalues, then A is diagonalizable. So let's say if you have 3 columns or 3 unknowns. So if you have 3 different eigenvalues, definitely you have 3 bases for it, and hence it is diagonalizable. Then for this example, the A you should have 4, 2 plus square root of 3 and 2 minus square root of 3. So these are the 3 distinct eigenvalues. So you should have the 3 bases because each of the eigenvalues would give you at least 1 basis. And then we have another tip for the diagonalizability of a triangular matrix. So in the previous lesson, we learned that if A is an upper or lower triangular matrix, then the eigenvalues will be the entries along the diagonal. So in this case, if this is the upper or lower triangular matrix, just need to know how many distinct diagonal entries. So -1, 3, 5, and -2. No repetitions of the eigenvalues. So we can directly say that A is diagonalizable because we have 4 different eigenvalues corresponding to 4 columns here. So the number of unknowns and the number of eigenvalues are the same. So one of the applications of this, the diagonal matrix P, is such you can use it to calculate the power of a matrix. So let's say A raised to the power of 2, you have A raised to the power of 4, you have A multiplies with A 4 times. So this calculation is quite tedious where you need to deal with a lot of multiplications. Whereas from these expressions, P inverse AP equals to the diagonal matrix, you can utilize these expressions or equation to find out the power of a certain matrix. So let's look at the derivation here. So P inverse AP raised to the power of 2. So you have P inverse AP multiplied with P inverse AP. Then we know that P multiplied with P inverse will give you identity. Identity is you can cancel out. So A with A, so it's A squared equal to D squared. So this should be the case here. And then you have the P inverse and P here, right? So we need to get rid of the P inverse and P here, such that you only have A2 here. So you multiply both sides with P inverse, P and P inverse, such that you have this expression. So this is the expression or the equation that you are going to use for the calculation of the A raised to a certain power. Because you just need to deal with the P inverse, which is a straightforward matrix obtained from the eigenvectors, and the D raised to the power of n is basically just the entries or the eigenvalues raised to the power of n. So you don't need to repeat the multiplications of the matrix for many times. So this actually saves the time for you to find out the power of a matrix. And beware of the sequence of P. For diagonalization, we have the P inverse AP equals to D. For power of a matrix is that AN equals to P D raised to the power of n and P inverse. So these two equations are almost similar because all the terms are the same. It's just that the sequence of the P inverse and P here, you must be careful. So this is one of the example here. If you had the original matrix A and the P where we found out in the previous case, and the D here. So to find the A raised to the power of 13 is basically you just multiply the P vector and raise the power of the entries along the diagonals for the diagonal matrix to 13 as well. Then multiply with the P inverse. So this is quite straightforward compared to having to multiply the A